Hi there, I'm graduate teaching assistant Aldo Sanpedro, and I will be doing a walkthrough of a standard tri-hybrid 3-point test cross. This is problem number 13 from Chapter 5 in Genetic Analysis 3rd edition. I will review how to perform a chi-squared test, determine gene order, calculate recombination frequencies, and determine interference. Before we jump in, I will note that I will walk through each question, A through E, at the end once we obtain all of our required information. My intent is to share a thorough method for solving 3-point test crosses that will also provide a framework for relating theoretical knowledge. If you are feeling confident, feel free to skip to the end of this video to check your answers. Let's dive in. My first objective is to duplicate the table to the left and simplify the phenotypes into characters that make solving this problem easier. Here, I transfer the progeny numbers and total progeny. Next, I replace phenotype traits with their corresponding character as described in the question to make life easier. I prefer to work by column. I'll replace colored with a capital C. I label colorless as lowercase c. I label full with a capital S. And shrunken with a lowercase s. The same technique follows for waxy and starchy. Capital W and lowercase w are used respectively. Next, I will describe each phenotype pair, C and S and W, and C and W, as recombinant or parental. This will make calculating recombination frequency much easier. I create columns for each pairwise interval, C and S and W, and C and W. The next step is to identify the parental trait intervals, so that we can discriminate between parental and recombinant pairs. Our parental phenotypes are inferred from the question description and the most common progeny. Our parental intervals are homozygous dominant, capital C, capital S, and capital W, and homozygous recessive, lowercase c, lowercase s, and lowercase w. Next, I assign whether a pairwise trait interval is parental or recombinant. If the phenotype pair matches the parental phenotype pairs, I denote that pair with a capital P. For instance, capital C and S pairs are parental, as are lowercase c and s pairs, so I assign those pairs with a P for parental in the corresponding column. Then, I label any phenotype interval deviating from either of the parental phenotype pairs with an R for recombinant. I repeat these steps for the next pairwise intervals, S and W, and C and W. We're almost ready to calculate our recombination frequencies. Before we do so, let's evaluate our gene order first. Establishing the gene order will help us identify 2 additional recombinant intervals that stem from double crossover events, and ultimately factor into our recombination frequency calculation. An assumption we make when solving 3-point test crosses is that the least number of progeny groups result from double crossover DCO events. 4 kernels from colored, shrunken, and waxy, capital C, lowercase s, uppercase W, and 2 kernels from colorless, full, starchy, lowercase c, uppercase s, and lowercase w descend from DCOs. The gene order can be determined by comparing the DCO trait intervals to the parental gene intervals. Progeny will differ by only one of the loci. In our question, that loci is S. Thus, loci S is in between flanking loci C and W. Now that we understand our gene order, we can evaluate the entire C-S-W interval for recombination frequencies. The 2 new C-S-W interval recombinants are located in our DCO progeny. Once again, these intervals can be reclassified as recombinant only because we have determined the gene order from our double crossovers. We confirm that locus S lies in between loci C and W in the C-W interval. We're finally ready to move on. My first step in calculating each recombination frequency is to sum all recombinant progeny for each interval. For interval CS, I sum 116, 4, 2, and 113. Our sum is 235 recombinant progeny for interval CS. I then use the same method for interval S and W, and I sum 601, 4, 2, and 626. Our sum is 1,233. I do this again for interval CW. However, I multiply the DCO recombinants by 2, since they each represent 2 recombination events. Our sum is 1,468 for interval CW. Our next step is to divide the recombinant progeny from the total progeny for each interval. We then multiply by 100 to obtain our recombination frequency percent, centimorgans, or map units. For interval C and S, I divide 235 by 6,708 and multiply the quotient by 100. I get a recombination percent of 3.5. For interval S and W, I divide 1,233 by 6,708 and multiply the quotient by 100. I get a recombination percent of 18.4. For interval C and S, I divide 1,468 by 6,708 and multiply the quotient by 100. I get our final recombination percentage of 21.9%. With this information, we can now construct a genetic map, as percent recombination frequency is equal to centimorgans or map units. I construct a chromosome using our gene order C, S, and W. Interval C through S is 3.5 map units apart, whereas interval S through W is 18.4 map units apart. Interval C through W is 21.9 map units apart. Note the map units for intervals C through S and S through W are approximately equal to interval C through W when summed. What about interference? Recall that interference measures the independence for a crossover event that is potentially influenced by a separate crossover event. Interference, I, is equal to 1 subtracted from the coefficient of coincidence, COC. COC is inversely related to interference and thus expresses the extent of interference. No interference occurs when I is equal to 0. A negative interference value indicates that there are more double crossovers than expected. Meanwhile, interference values greater than 1 indicate that one crossover event suppresses another. The COC is determined by dividing the observed DCO count by the expected DCO count. We can calculate the expected DCO number by multiplying our total progeny number by the product of our 2 single crossover recombination frequencies. For our problem, I start by setting up the formula and fill it accordingly. Our observed DCO numbers are 4 and 2. These values are circled on the table to the left. To calculate our expected DCO number, I multiply the recombination frequency of interval CS 0.035 by the recombination frequency of interval SW 0.184. This product is multiplied by 6,708, our total progeny number. We obtain an expected DCO number of 43.2. Compare this to the observed 6. Finally, I subtract 1 from the quotient of 6 and 43.2 to obtain our interference value of 0.861 or 86.1%. Because our interference value is in between 0 and 1, we can conclude that a single crossover event is interfering with another crossover event, but not completely suppressing it. That wraps up interference. Let's move on to doing a chi-squared test. A chi-squared test will enable us to explore whether or not our data show a significant deviation from the expected data distribution. For our Testcross involving a trihybrid and a homozygous recessive individual, we expect 8 classes to appear, each representing 1/8 the total number of progeny. In our case, this means that we expect each class to represent 838.5 individuals. We can immediately deduce that this is not the case. We will now walk through the steps of a chi-squared test to statistically determine if our data show significant deviation from the expected data distribution. I write the formula here to determine our chi-squared test statistic for a given degree of freedom. It is equal to the summation for each phenotype class of the squared value of observed instances subtracted by the expected instances divided by the expected instances. I'll begin filling the formula for each phenotype class. Given that our expected progeny number is equal to 838.5 as determined earlier. You can see that this is a lot of work. Careful calculator use can save you a lot of time. I'm now ready to proceed by summing all these expressions. I get a test statistic value equal to 10,649 and 7 degrees of freedom obtained from subtracting our number of classes, 8, by 1. If our test statistic and degrees of freedom correspond to a p-value less than 0.05, we can reject the chance hypothesis and conclude that there is a significant difference between our observed and expected results. This is a table that will help approximate our p-value based on the test statistic and degrees of freedom we feed it. For 7 degrees of freedom, our test statistic is greater than all the test statistics listed here. Thus, we can conclude that our p-value is less than 0.01. This rejects our chance hypothesis and statistically validates our statement that the observed results significantly deviate from the expected results. Using a dedicated p-value calculator, we obtain a p-value less than 0.00001. The lower the p-value, the less valid our chance hypothesis is for this question. We can safely reject the chance hypothesis. Now, I'll move on to answering each question subset for question 13, now that we have all of our required information. A. Why are these data consistent with genetic linkage among the 3 genes? All recombinant progeny are rare when compared to parental progeny. Meanwhile, recombination frequency is much lower than 50% for all genes, demonstrating linkage for the 3 genes. B. Perform a chi-squared test to determine if these data show significant deviation from the expected phenotype distribution. Our chi-squared test supports that our data show significant deviation from the expected data distribution with a p-value less than 0.01. We reject the chance hypothesis. C. What is the order of these genes in corn? Recall that we determined earlier that the gene order is CLSHWX. This is because double crossover gametes, capital C, lowercase s, uppercase W, and lowercase c, uppercase s, lowercase w, differ only at the S locus. Due to this, the S locus corresponds to the middle, or in this case, the SH locus. D. Calculate the recombination frequencies between the gene pairs. We determined these earlier, however we calculated percent recombination frequency. Our final answers for this question are in decimal form. This question does not ask us to build a gene map, but let's build one anyways. Once again, note that the distance between C and W is approximately equal to the sum of distances for C and S and W, because it represents the whole interval. E. What is the interference value for this dataset? We solved this earlier and obtained an interference value of 0.861. A value between 0 and 1 indicate that interference is occurring. 0.861 indicates that a crossover in one region interferes with the formation of a crossover in another region. That's all for question 13, A through E. Thanks for joining in, and feel free to reach out with any questions or comments.